We're going to have a look at how to do a two-sample t-test here. So I've made us some rather contrived data, which could be it could be the heights of students, it could be weights gained by fish in a trial, it could be absorbances from cells in two different cultures, whatever. The important thing is about the data for a two-sample t-test is we've got to have quantitative data. If I'd have had my samples arranged in interval order, first, second, third, fourth, for example, then I couldn't do a t-test. If my data is categorical, red, green, blue, or something, then I couldn't do a t-test. I've got to have quantitative data. Okay. You can see then I've got my data arranged in two columns. Here's sample 1 and here's sample 2. Another way we could have the data arranged in Minitab. If I go and stack the columns, I can show you another way of having the data arranged, and it would still work. The t-test would still work. So you can have your data in one of two ways for Minitab to do a t-test. So look here that we've got then the data here, and then we've got the samples there. Either way is going to work for having your data to do a two-sample t-test. Either a sample per column, as we've got here, or your data all in one column, your response variable, your dependent variable in a column here, and your independent variable, or your categories, sample 1 and sample 2 are the two categories here in the next column. As we go on to do analysis of variance, for example, then it becomes much more important to have your data in a single column, your response variable in a single column, and then your predictor variables in separate columns. So for example, I could have got sample 1, sample 2, and I could have then got rearing condition 1, rearing condition 2. So I've got 20 sample 1s, 10 of them could have been in rearing condition 1, 10 of them in rearing condition 2. That shows me why I would need my data to all be in a single column. Let's work though for this time, for ease, in having our samples in two separate columns as we've got here. Okay, so let's have a look at this data then. Let's see what we can glean about this data. So I'm going to produce an interval plot where I want to see sample 1 and sample 2 compared to each other. We'll select those two in there. So because this is made up data, I don't know what my units are on the side, but if I said before, heights of students, a 20 centimetre high student, that's a rather bizarrely proportioned individual. It doesn't matter. It could, like I said, it could be weight gains in fish, it could be absorbances of from cells in different culture conditions. Doesn't matter. We can see that the two samples are here. Here is the mean of sample 1 and the mean of sample 2, and then we've got the 95% confidence intervals of the mean, which says if I was to go back and resample the population from which sample 1 and sample 2 came from, if I was to do that 100 times, 95 times the mean of those 100 samples, 95 of those means would be within these confidence intervals here. So what we can see is the two confidence intervals overlap a little bit. So we don't fully know here, is sample 1 and sample 2 statistically significantly different from each other? And it's that the t-test can help us to do. Okay. So there's some assumptions of the t-test. Firstly, we need sample 1 and sample 2 to be both normally distributed. Easiest way to do that is to go and get a graphical summary of both sample 1 and sample 2. And I can then look at the Anderson-Darling test for both, and I can see is my data for sample 1 and for sample 2, is the data normally distributed or not? So I'm looking up here at the Anderson-Darling normality test. The null hypothesis of this Anderson-Darling normality test is that the data distribution is not significantly different from 0. And recall, if the p-value is greater than 0.05, I'm going to fail to reject my null hypothesis. So say that again. The null hypothesis is that the data distribution is not significantly different from 0. P is greater than 0.05, so I fail to reject that null hypothesis. So really crudely speaking, I can say no evidence that either sample 1 nor sample 2 have got any departure from normality. The fact that my sample size is 20, look at the ends, I can see that I've got the Anderson-Darling test is pretty powerful when the sample size is around 20. When it's much above 15, I can have a fair bit of faith in the Anderson-Darling test. And then I've got my other descriptive statistics here. I can see the mean of sample 2 is 18.768. The mean of sample 1 is 19.664. The other descriptive statistics shown in this graphical summary for me here. I can also then see the two variances. 1.387 is the variance for sample 1. 1.427 is the variance for sample 2. There's another important assumption of the t-test. We need to do a statistical test called Levene's test to make sure there is no statistically significant difference between those two variances. If there is, then we need to adjust our t-test a little bit, which I can show you how to do. So we need to do another test before we can do the t-test. I've done my two Anderson-Darling tests. I need to do a Levene's test now to see if there's significant difference in those two variances. So to do that, I go to do a two variance test here. And I'll go to here, look, each sample is in its own column. Sample 1, well, that's the one that says sample 1, and sample 2 I'd put there. Alternatively, look, I could have both samples are in one column. Well, here that's where I'd have samples would be the data, and sample IDs would be the samples here. But we'll stick to it this way because it's easier. Sample 1 and sample 2 goes in there. Right. So what we're looking for now is another hypothesis test. And the null hypothesis here is that there is no significant difference between those two variances. Remember those two variances that we saw on the descriptive statistics on the graphical summary a moment ago? We're wanting to know, is there any significant difference in those two variances? Because that's a really important assumption of the t-test, that the variances are not different from each other. Again, we would reject the null hypothesis of this Levene's test here if the p-value is less than 0.05, which it isn't. It's way above 0.05. So the null hypothesis that there's no significant difference between the two variances, we fail to reject. So we can say we've got two normally distributed samples, or well, be careful, we've got two samples which we've got no evidence of non-normality of their distributions, and we've got no evidence of unequal variances. So we're okay to go into the t-test to test the null hypothesis that there is no significant difference between the mean of sample 1 and the mean of sample 2. So to do the t-test, we go to do a two-sample t-test here. And look, we've got the same issue. Both samples are in one column, like in C4, and the sample IDs are in C5, but I'll just select, for continuity, for what I've been doing, that each sample is in its own column. Sample 1, and sample 2, there. I'm going to go into options here. Now look at this little box down here. Assume equal variances. Here we're telling Minitab, the stats software, to run a t-test that assumes the variances are equal. We did the Levene's test here, and we've got no evidence of non-equal variances. So Minitab can assume the variances are equal. Okay? And we will then do our t-test as follows. Remember, the null hypothesis is that there is no significant difference between the mean of sample 1 and the mean of sample 2. The alternative hypothesis is that there is a significant difference. So that is then summarized here. Look, the null hypothesis, H subscript 0, is that mu1 minus mu2 equals 0. Mu1 simply means the mean of sample 1. Mu2 is the mean of sample 2. If those two means are really similar to each other, mu1 minus mu2 is going to be 0 or very close to. Here we've got the equal sign taking on a funny meaning of being not statistically significantly different from, rather than being exactly equal to, like perhaps we would see in arithmetic. 2 and 2 equals 4 in arithmetic. Well, in statistics, 2 and 2 equals a number that's not statistically significantly different from 4. The alternative hypothesis h subscript 1 is that mu1 minus mu2 does not equal 0. In other words, there is a statistically significant difference between the mean of sample 1 and the mean of sample 2. Okay. We've got some descriptive statistics up here. Look, n's, means, standard deviations, and the standard error of the mean. I've then got that mean difference. Mu1 minus mu2 isn't arithmetically equal to 0. No, in fact, it's arithmetically equal to 0.896. If I take 18.77 minus 19.66, I'm going to get 0.896. That's the pooled standard deviation, which is sort of like the average of those two standard deviations with some error about it. Down here is the bit that we're interested in. This is the value of t. This is what we've computed. The t-test is a formula that I don't need to bore you with, but it's t equals. So Minitab has computed a formula. T equals 2.39 once we've done all the arithmetic. The degrees of freedom we work out by the number of observations in sample 1 minus 1 plus the number of observations in sample 2 minus 1. So that's 19 plus 19 gives me 38. That's the degrees of freedom. So the value of t at 38 degrees of freedom, the probability of getting that value or greater if the null hypothesis is true is a p-value of 0.022. So that is a p-value below 0.05. So because it's a value below 0.05, we're going to reject this null hypothesis. And we're going to go with our alternative hypothesis. We're saying the alternative hypothesis is going to be, we've rejected the null, forcing us to go with the alternative hypothesis at the 0.05 significance level. So we can go back to our graph, wherever it's gone. No, wrong one. There. And we can now see that there is in fact a significant difference between those two means. Though these two confidence intervals overlap, they're not overlapping enough to give us I've lost it again. There it is. Let's just make it a bit smaller. There we go. So we can then see that there is a significant difference in these two means. Now we would write that as follows. If I go and annotate this graph, we could add here that t equals 2.39, p equals 0.022. Now what I'd need to do as well, next to my t, I've got to add the degrees of freedom. And what we'd normally do in a scientific paper, if we were reporting these statistical results correctly, is we'd use a subscript now. But I can't do a subscript in these text boxes in Minitab, so I'm just going to put it in brackets. Now I'm going to say T38, T in brackets 38. What we really should be presenting that is T subscript 38 equals 2.39, which we've got from there. The degrees of freedom, that's what the T statistic was computed as at that many degrees of freedom. Say again, the probability of getting that T statistic 2.39 at 38 degrees of freedom, if the null hypothesis is true, is that p-value, less than 0.05, so I reject my null hypothesis. There we go.